In today's reading, we really have one main goal, which is to define what we mean by real numbers, at least in this class. But in doing so, we're going to go straight to the heart of some of the biggest ideas in analysis. And so today is when the analysis of the class really starts. So a major component of this course is to formalize the notion of what we mean by a limit. You will have encountered these in calculus classes, but usually it's only dealt with vaguely. The intuition we've developed so far about the real number system tells us that a real number should be a limit of rational numbers. But what does that mean? Again, the intuition is that we imagine we can find better and better approximations to our real number using rational numbers. Now, assuming we know what real number we started with, what that means is we have a sequence, x1, x2, x3, and so on, and these are rational numbers, such that for any arbitrarily small error, so we're going to imagine setting a very small distance away from our limit, and that error will be written as 1 over n. Here you should imagine that n is a large natural number. There exists another natural number m, such that the absolute value of x, our limit, and xk, the kth term in our sequence, is less than 1 over n whenever k is greater than or equal to m. So we can go far enough out in the sequence that the difference between the terms of the sequence and the limit is as small as we like. Now, our book uses 1 over n, and where n is a natural number. There's a reason for that, and I will stick with that convention. But you will see in most other texts that this error, instead of being called 1 over n, is called epsilon, using the Greek letter epsilon, which looks like a variation of e. And so you'll hear that term elsewhere, but we'll be using 1 over n. So what we really have to do is 3 tasks just right away. So the first thing is we want to say how it is we can tell that a sequence of rational numbers is approximating something. That means it has a limit or should have a limit without knowing what the limit is ahead of time. The second thing is to determine when 2 sequences of rational numbers should approximate the same real number. So they should have the same limit, but again, we won't know what the limit is. And then the third step will be to define real numbers using sequences of rational numbers that should have a limit, and then to assume that if they should have the same limit, in a sense we'll see later, then they'll give us the same real number. And then what we'll do is we'll define the real numbers to be the things that sequences of rational numbers approximate when those sequences are approximating something. This is a somewhat tautological definition. It sounds like we're just saying the thing that we're defining. But that's just a consequence of the way we've built this up from our intuition. And we'll see in finer detail what that means. The first thing to think about is what it means to have a sequence that should have a limit. Not every sequence of rational numbers can be reasonably said to approximate something. If you think about the sequence 1, 10, 100, 1,000, that just keeps growing and growing, there's nothing that's approximating. Or even just a sequence that's going back and forth between 2 numbers, like 1, 0, 1, 0, 1, 0. Really, in order for a sequence to approximate something, its terms have to be getting closer to each other, and they have to be getting closer together in a fairly strong sense. So the first formal definition we need for today is that of a Cauchy sequence. Cauchy was a French mathematician. That's why we pronounce his name that way. So a sequence of rational numbers, x1, x2, x3, and so on, is a Cauchy sequence if for any error, 1 over n, so remember we're thinking of n as large, so this is a small amount, there exists some m such that the absolute value of xj minus xk is less than or equal to 1 over n whenever j and k are both greater than m. So n here is we're using to control our error, and m is telling us how far along we must go in the sequence, and then j and k are telling us we can look at terms past that point labeled by m. Now, I won't do this often, and you won't ever see the book do this, but I've also written this definition out symbolically just to highlight a couple of things. And the main thing being that this is a definition that has 4 quantifiers in it. And this may be the first time you've had to wrangle something like that. So if it feels like this is a somewhat complicated definition, it is. But this is what we need in order to clarify the ideas that are coming. So with some practice, you'll feel more confident working with all these quantifiers. So in symbols, what the definition says is, for every n, there exists an m, such that for every j and for every k, if j is greater than or equal to m and k is greater than or equal to m, then the absolute value of xj minus xk is less than or equal to 1 over n. Okay, so then you can see all that all at once. Now, the important thing about this definition is that it has no reference to a limit. We don't have to know what the limit is ahead of time. But it does take a bit of work because of that to show that some sequence meets the Cauchy criterion. So let's look at an example. Let's suppose that our sequence has x sub k equal to 1 over k. So it starts out 1, 1/2, 1/3, and so on. We want to make sure that the absolute value of xj minus xk is small when j and k are large enough. So when j and k are indicating we're far enough out in the sequence. So let's look at that expression, the absolute value of xj minus xk. Since xk is 1 over k, xj is 1 over j. So we're looking at the absolute value of 1 over j minus 1 over k. Now we can rewrite that as the absolute value of 1 over j plus the opposite of 1 over k. And then using the triangle inequality for rational numbers, that would give us that is less than or equal to the absolute value of 1 over j plus the absolute value of minus 1 over k, which is the same as the absolute value of 1 over k. So what that means is if both j and k are bigger than 2n, okay, so if j and k are bigger than 2n, then the fractions at the end of this this expression in the middle of the page, each of those will be less than 1 over 2n. And so the expression, the absolute value of xj minus xk, will be at most 1 over 2n plus 1 over 2n, which is 1 over n. And so for every n, every natural number n, that's going to dictate our error, if j is greater than or equal to 2n and k is also greater than or equal to 2n, then the difference of 1 over j and 1 over k is less than 1 over n in absolute value. So effectively what we've said, we figured out what m has to be. We've said that m in the Cauchy criterion can be 2n. And that's fine. The criterion says that m can depend on n, which makes sense because if you want the terms to be, you want the error to be smaller, you're probably going to have to go further out in the sequence. Now the fact that we could, when we were finding this upper bound, we could get rid of that minus sign in front of the 1 over k, suggests that maybe we might actually been able to do better. This is a fairly soft estimate, but this is enough now to provide us with an example. Another example is that decimal expansions give us Cauchy sequences, which is good since we often think about real numbers in terms of their decimal expansions. But I'm not at this point saying that every real number has a decimal expansion. We haven't even defined what a real number is yet. But how does this work? If we take a decimal expansion such as 3.14159.265, the decimal expansion for pi, that will produce a sequence that starts out 3.1, 3.14, 3.141, 3.1415, and so on. Each of these is a rational number. It can be written as some integer divided by a power of 10. And more generally, the decimal expansion A0.A1, A2, A3 will give a sequence that starts out A0.A1, A0.A1, A2, and so on. So the question then to ask is, why is this a Cauchy sequence? Well, if you specify up until the kth decimal position after the digit after the decimal point, then after that, any two numbers, they're going to agree in those first k positions as well as whatever came before the decimal point. And so their difference will be at most 1 over 10 to the k. And so what that means is in the Cauchy criterion, we could take m to be anything larger than the base 10 logarithm of n, which would tell us how many digits we had specified. So we'll talk more about decimal expansions in a little while, but I just wanted to use that as an example of how we can get Cauchy sequences. The second step we need is to tell when two sequences should be approximating the same thing. So conceptually what that means is their terms are getting close to what their common limit is, but we don't know what that is yet. And so they should at least be getting close to each other. And that's what our second definition then tells us. Two Cauchy sequences of rational numbers, say x1, x2, x3, dot, 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 and y1, y2, y3, dot, 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 will be called equivalent if for every n, specifying the error, there exists an m specifying how far in the sequences you need to look, such that for all k greater than or equal to m, we have the absolute value of xk minus yk is less than or equal to 1 over n. And notice in this definition, we don't have to look at two different places in the same sequence. We're looking at the same position, the kth position, in two different sequences. So there's a couple of examples. We'll think more about these in the future as well. These two pairs of sequences are equivalent. 1, 1/2, 1/3, 1/4, and so on is equivalent to the sequence that just is 0, 0, 0, 0, 0. And the sequence 0.9, 0.99, 0.999, and so on and so forth, is equivalent to the sequence 1, 1, 1, 1, 1. So that's worth thinking about, and maybe we'll bring that up in the discussion. A little lemma we need at this point is we've called this equivalence. We want to make sure that that name is justified. And so the lemma says that equivalence of Cauchy sequences of rational numbers is itself an equivalence relation. Remember, an equivalence relation has three properties. First of all, it has to be reflexive. Any sequence must be equivalent to itself. It must be symmetric. If x1, x2, x3 is equivalent to y1, y2, y3, then the reverse has to be true as well. y1, y2, y3 has to be equivalent to x1, x2, x3, and so on. Now, the book says that these two properties should be obvious to see. I don't like using that word. I prefer to stay away from it. But you should think about why these properties follow from the definition that we've given. And then the third property is that in the equivalence relation, the relation must be transitive. So that means that if we have three sequences, and the first is equivalent to the second is equivalent to the third, then the first is equivalent to the third. And there is a proof of that property in the book. And now finally, we're ready to make our definition of what we will mean by a real number. So a real number is an equivalence class of Cauchy sequences of rational numbers. So we've taken our idea of approximating by rational numbers and now turned that into our definition for what a real number should be. And if one of these equivalence classes, say x, has a particular representative by rational numbers, x1, x2, x3, then we'll say that that sequence of rational numbers converges to the real number x. And so what this definition means is that any two equivalent Cauchy sequences of rationals will converge to the same real number. They're equivalent, so they're in the same equivalence class, and that is the number that they will converge to. And now we define the real number system, which is what we were aiming for, to be the collection, we write this as R, of all equivalence classes of Cauchy sequences of rational numbers. Now, we've seen before that the rational numbers contain the integers. We can take any integer and give it a denominator of 1 that produces a rational number. And in the same way, the real number system contains the rational numbers. We can take any rational number and just identify it with the equivalence class of the constant sequence, where we just repeat that rational number again and again. So this is a definition we're going to be thinking about over the next few classes. It might not be clear that this has all the properties that we expect real numbers to have. We might wonder how to add and multiply them, for instance, or how to tell when one is bigger than another. But those will be the focus of the next couple of readings. So I will end here.